Welcome back to the course Basics of Mechanical Engineering 2. We have discussed non-conventional machining processes in this week, and I will take a tutorial on the same. We have classified the non-conventional machining processes into three major categories. One is based upon the mechanical energy, then based upon the chemical energy, then based upon electrical energy. In the combination of electrical and chemical, there is also electrochemical energy. Now, in this tutorial session, I will take one of these processes, each mechanical, electrical and chemical, and try to take the problem statements on that. I am Dr. Amandeep Singh Oberoi from IIT Kanpur. So, just to recall, ultrasonic machining process, which is a mechanical energy based processes or mechanical based processes in which abrasive particles flow through this vibrating tool here. This tool is given here, and this turns into a slurry when we add some water or some liquid here, and based upon the size of the abrasive particle, based upon the parameters which we will discuss now, that is the volume of what material removal impact, the number of particles and the frequency, the material removal rate is obtained. And how do we calculate the material removal rate? Let us try to see this. Volume of work removal rate denoted by Q is proportional to V, Z and nu, where volume V is the material removal per impact, which is in millimeter cube. Z is the number of particles making impact per cycle. Then nu here is frequency. So, it is generally said that with an increase in static loading material, removal rate tends to increase initially, but after a critical value of the force, that is MRR, starts to decrease, because under high forces grains start getting crushed. So, in the beginning itself, the particles are completely sharp, the abrasive particles, as it was thought that particles are considered spherical here. So, those are sharp. So, at a certain specific rate, specific level, if I try to plot it here, after some specific critical value of MRR, the decrease comes. For example, if I have feed force here, feed force S, and I have MRR which is Q in this direction, it is something like this. It increases at certain level, and then the particles become blunt and it becomes crushed, it starts decreasing then, something like this. So, from here it is decreasing. So, this is the maximum MRR, maximum. So, let me try to see the problem statement here and try to use the relation that we saw in the previous slide. In ultrasonic machining setup, that operates at a frequency of 25 kilohertz with a abrasive particles number as 6000, making an impact per cycle. With 6000 abrasive particles, that makes an impact per cycle. The volume of material removal rate of impact is 1.8 into 10 to the power minus 6 millimeter cube. The total number of impact per second is to be calculated, material removal rate is to be found, the MRR in millimeters cube per minute is to be found. We have been given here frequency nu is equal to 25 kilohertz, number of particles impacting per cycle, that is value of Z is given 6000, and volume removed per impact, that is V is also given, that is 1.8 into 10 raised to power minus 6 millimeters cube. So, when I say 25 k hertz, it is 25,000 cycles per second. First part is total number of impacts per second, that is part A, number of impacts per second, this is equal to Z into nu, that is equal to 6000 into 25,000, this is equal to, there are 6 zeros, and 6 into 25 is 150. This big number which gives me 150 into 10 raised to power 6 impacts per second as my answer. Next part is material removal rate, MRR. MRR that we saw is Q, this is equal to V into Z into nu. This is equal to 1.8 into 10 raised to power minus 6 into Z into nu, that is already calculated here. This is 150 into 10 raised to power 6, and this is in now millimeter cube per second. So, directly we can say 150 into 1.8 is equal to 270 millimeter cube per second, because this 10 raised to power minus 6 and 10 raised to power 6 cancels with each other. Then comes the MRR in millimeter cube per minute. We have calculated Q as 270 millimeter cube per second. If I need to convert this into minutes, I will just multiply it by 60. 270 into 60 millimeter cubes per minute, that is 16200 millimeters cube per minute. So, this was calculating the MRR and number of impacts per cycle. This is another problem statement in the similar way, in which we have been given an ultrasonic machine is removing metal at a reported MRR of 10,000 millimeters cube per minute. This is reported from the past data, that is, this is secondary data. And the primary calculation is to be taken now. The process parameters are as follows: frequency is 22 kilohertz, number of particles impacting per cycle is 5000, volume removed per impact is 2 into 10 raised to the power minus 6 millimeter cube. Verify if the reported MRR is correct, that is secondary data is given. We need to generate a primary data that is taken through calculations, that is experiment. These parameters are given. First part is to compare the MRR with the given one, that is 10,000 millimeter cube per minute, and second part is if the frequency increases by 20%, what is the new MRR. Third part is if the abrasive particles per cycle is reduced by 10%, what happens to MRR. Let us try to see this. We have been given here given MRR is equal to 10,000 millimeter cube per minute. The value of nu is 22 kilohertz, that is 22,000 cycles per second. Then number of particles per cycle, that is Z is equal to 5000, and volume removed per impact is given as 2 into 10 raised to the power minus 6 millimeters cube. So, first part is verify MRR. Have been given the values here. Let me calculate the MRR. Q is equal to VZ into nu. This is equal to 2 into 10 raised to the power minus 6 into Z is 5000 and nu here is 22,000. This value comes down to be 220 millimeters cube per second to convert this into millimeter cube per minute, so I will call it MRR per minute is equal to 220 into 60, that is equal to 13,200 millimeters cube per minute. So therefore, the experimental MRR is 13,200, and compared to the given value, that is 10,000, it is 132% of the given data, that is MRR that is given. I will write MRR given here as well. The next part is, if the frequency increases by 20%, what is new MRR? Increase of the frequency by 20%. So let me put part B here. Frequency increases by 20%. That is now nu dash is equal to 1.2 times of nu. This is equal to 1.2 into 22,000. This is equal to 26,400 cycles per second. Based upon the nu dash, let me calculate the new MRR. Q dash is equal to Vz into nu dash. This is equal to 2 into 10 to the power minus 6 into z, that is 5,000, into nu dash. Nu dash is 26,400. This gives me the value of MRR in millimeter cubes per second here as of now as 264 millimeter cube per second. So Q dash in millimeters cube per minute is equal to 264 into 60 millimeters cube per minute. This is equal to 15840 millimeters cube. Now there is rise in MRR. MRR is now 15,840 millimeters cube per minute. The calculated value was 13,200 millimeters per minute with the base value of nu. When nu is increased by a certain times, for example, it is said that 20% increase is there, and it is directly proportional to the MRR as it is given in the formula you can see here. It is directly multiplied here. If you calculate this, 15,840 would be the 20% rise of the base MRR, that is 13,200. So this is also a 20% increase. I did all the calculations, otherwise you could have put here 1.2 times of nu is nu dash, and based upon q and q dash you can even calculate it. It has q dash is equal to 1.2 times of q. This could also be direct answer. Now the next portion, they say if number of busy particles is reduced by 10%, what happens to MRR? Now number of busy particles are reduced. Let us calculate this in a direct form. Number of busy particles reduced by 10%. That is now z dash is equal to 0.9 of z, 10% reduction. I will put here q double dash is equal to v into z dash into nu. So here q double dash, if I put the value of z dash here directly, value means as comparison to z it is v into 0.9 into nu. So, q double dash is equal to 0.9 of v into z into nu. That means q double dash is equal to 0.9 of q. So, to calculate this, q double dash is equal to 0.9 into the value of q you can put here, and it is also 90% of the original value. If I put the value of q here, so this value will come out to be 11880 millimeters cube per minute. So, this was the ultrasonic machine, that is based upon the mechanical energy. Let me now try to see electrochemical machining, that is based upon the electrical and chemical energy both. So, here let us recall the concept of electrochemical energy or electrochemical machining. I will also take this in the virtual demonstration that how the process is running. So, this is just a recalling of the process. In electrochemical machining, we have this setup where workpiece is machined using a tool and constant feed to the tool is given. There is also electrical connection. The workpiece is anode and tool is cathode here. We have electrolyte filled in the tank. This is a tank where electrolyte is filled, and both electrical and chemical energy work together. MRR here remains unaffected by workpiece hardness, so making ECM very ideal for low machinability materials and complex materials, because hardness is not the concern here. There is virtually no tool wear actually, but because of the rusting, some deterioration to the overall components of the system do happen. So, electrochemical machining is an advanced non-contact machining process, again like EDM that we have discussed. In this process, the electrolysis process is governed by the Faraday's law. The amount of material dissolved from the anode is proportional to the amount of current passed. The amount of different substances dissolved by the same amount of current is proportional to the gram equivalent weight of the material. So, this is gram equivalent weight m, which is proportional to I, T and epsilon, where here I is the current in amperes, T is time in seconds, epsilon is gram equivalent weight of the material, F is Faraday's constant, and rho is density of the work material in grams per centimeter cube. So, this is equal to I T epsilon by F. So, here in ECM both tool and workpiece experience significant forces due to high pressure fluid in the gap. So, that is Faraday's law here govern the process, so stating the material removal rate is directly proportional to the electric charge being passed here. The different substances dissolve or deposit in the proportion to the chemical equivalent weights. A certain advantage is surface finish up to 25 micron could be achieved in the ECM process, and the gram equivalent weight here is the ratio of the atomic weight and valency of the material, that is epsilon is equal to A by Z. So, we can put here the m is equal to A I T by Z into F in grams, and m dot is the mass flow rate. This is equal to A I by Z into F, this is grams per second. So, MRR, that is Q is equal to AI by Z F into rho, that could be put as epsilon I by F into density, and all the notations have been given in the previous slide here. Rho is density of work material in grams per centimeter cube. So, that is why the solution is given in centimeter cube per second. A hole of square shape having dimensions 5 millimeter into 5 millimeter is to be drilled in a copper block through ECM. Further, it is given that atomic weight and valency of copper are 63 and 1 respectively. If 5000 ampere current is passed for machining the block, then find the material removal rate in grams per second. It is very direct calculation. We know MRR here directly is equal to AI by ZF, that is equal to A into I into Z into F. Let me put the values directly. I have been given A as 63, I have been given A as 63 and I that is the current, that is 5000 amperes, Z is equal to the valency, that is 1, and F, that is Faraday's constant, that is 96500 coulombs. This gives me, while putting the values, 63 into 5000 by 1 into 96500, MRR is 3.26 grams per second. In the next problem statement, we have also been given density. Let us see what it says. It says in an ECM process, when MRR of 2 centimeter cube per minute is required, this is to be obtained using iron as workpiece, whose properties are given in the below table. What is the amount of current in amperes required for achieving this? The same relationship would be used here. We have been given the MRR already. MRR is equal to 2 centimeters cube per minute. Atomic weight A is equal to 56 grams. Valency Z is equal to 2. Density rho is equal to 7.8 grams per centimeter cube. So now we know MRR is equal to AI into ZF into rho. This is in centimeter cube per second. If I convert this MRR into the centimeter cubes per second, this will turn out to be 2 by 60, that is equal to 1 by 30 centimeters cube per second. So this gives me 1 by 30 is equal to A is 56, I is to be calculated, then Z is 2, F is 96500 and rho is 7.8 grams per centimeter cube. This gives me the value of I, it is the current as 896.07 amperes. Next comes the last topic of this session, that is electric discharge machining, EDM. Some of the authors do say that EDM is now no more a non-conventional process because it is so widely used in industry. But because the material removal rate is very low, that is why it is still talked in the non-conventional processes only. It uses electrical energy. The conventional processes uses the shearing force. Here we use the mechanical, the chemical, the electrical forces. But it was designed way back, a few decades back, and it is now widely used in different formats or different applications wherever it is required. So just to recall, so there is a tool and workpiece. Depending upon the shape of the tool, we get the shape of the workpiece. There is always spark gap that determines the MRR and the surface quality. So there is a DC pulse generator, certain components, if I say, that generates the pulse, and electrode tool is there, servo motor mechanism, spark generator, fluid is there, that is dielectric fluid. This kinds of EDM that you have studied is wire EDM, sinker EDM, or this is sink EDM, hole drilling EDM. Then certain advantage that we have seen, it gives high accuracy, that highly tight tolerances or minimal stress or vibrations are there when we try to use EDM. It creates intricate pockets, deep holes, thin walls, geometries that are very irregular or so. Hard material could be cut because minimum force is required, so their material only has to be conductive, that is the basic requirement. So these things we have discussed. Let me come to the resistance capacitance relations in circuit that I will use in the problem statements. We can, as can be seen from the figure, that the capacitor C here is charged by a variable resistance R by the DC source V0. Voltage across the work gap is same as the voltage across the capacitor, which varies with time. So V is given by the relation 1 minus e power minus t by RC. This times the V naught. When voltage reaches discharge voltage Vd, a spark takes place across a tool workpiece cap and thus discharging capacitor. I am not going into deep details here, just to give you very brief introduction of the EDM that is already discussed. Because this is basics of mechanical engineering course, we will only take very simple problems here, and these problems are only to give you introduction or a little details about how does EDM mechanism help. Let me directly come to the problem statement here. In RC circuit EDM, if capacitance and maximum charging voltage are 80 microfarads and 80 volts respectively, then calculate the spark energy in joule. This is an RC circuit, they say, and simply calculating E is equal to half C Vd square. So we have been given here C is equal to 80 microfarads, that is equal to 80 into 10 raised to power minus 6 farads. In Vd, the discharge voltage is also given here as 80 volts. Putting the values, energy becomes half of 80 into 10 power minus 6 into 80 square. This is equal to 0.256 joules. There is another problem that says, consider the following data regarding the RC circuit in the EDM process, where open circuit voltage is 100 volts, maximum discharging voltage is 70 volts, capacitance is 100 microfarads, and calculate the resistance for the idle time of 500 microseconds. The way it goes, the voltage versus time, if we suppose plot, so it charges across the capacitor, it charges like this, then it suddenly falls. This is the way it goes. This is charging, this is discharging. So we have been asked here to calculate R, charging resistance, with the idle time of 500 microseconds. So let us put the values which have been given. We have been given open circuit voltage V open as 100 volt, discharge voltage Vd as 70 volts, the capacitance C as 100 microfarads, and Tc, that is the idle time, is 500 microseconds. To put these values here, Vd is equal to V naught times 1 minus e power Tc by Rc. So putting the values, 70 is equal to 100 into 1 minus e power is the exponential of this is minus Tc by Rc, minus Tc is 500 into 10 raised to power minus 6 by R into C, R into C, that is capacitance is 100 into 10 raised to power minus 6. We only have to find the value of R here. R turns out to be 4.15 ohms. So this is our charging resistance. So, I have taken very basic problems and examples using the very basic formulas or relationships which are there in these three processes that I have used or taken in this lecture. There are details, each of the processes itself has its own complete books written. So, that is details of mechanical engineering or details of non-conventional processes, or maybe you can read a book on electrochemical machining itself, or maybe a research paper booklet that is available, handbook on these as well, which are available. So, this was about the non-conventional machining processes. I will now take the demonstration of the non-conventional machining, the virtual laboratory demonstration in the next lecture, and we will close this week. Thank you.